The derivative, instantaneous rate of change, and examples. So far in this section, we've motivated how we arrive at the instantaneous rate of change for a function. Ultimately, our goal is to be able to study functions, see how they change at every point, and use that to find out information about things that we're modeling or studying. One of the key things that we're trying to really understand is something called the derivative. So the derivative of a function is a function in itself. It's a function that tells us how much the original function changed at any given point. So for example, if we knew the derivative of a function and we plugged a number into the derivative, it would tell us how much that original function was changing at that point. And we could plug in whatever number we wanted to. So that's what we're trying to build up to, this derivative function, which will tell us the instantaneous rate of change for every single point of a function. Well, as you can imagine, it's related to the instantaneous rate of change because the derivative of f of x at the point A, which we can write as f prime of A, which you see here, is defined to be the instantaneous rate of change of f of x at the point A. So when we have the instantaneous rate of change at a point, it's also the value of the derivative at that point. So the derivative at a point is the same thing as the instantaneous rate of change. Now that's also the same thing as the slope of the tangent line. So as you can imagine, there's a lot of ways to talk about the same thing here. So this term, the derivative, is going to become very important to us. And the notation that you see here is something that we'll start to see as we work throughout this class. So again, the derivative is going to tell us how much a function changes at a given point, which is the same as the instantaneous rate of change. Example 1. Use the table below to approximate the instantaneous rate of change of f of t at 1, 2, 3, 4, and 5. So we talked a little bit before about approximating the derivative on a table. And the way that we went about doing that was by looking at the average rate of change to the left and to the right of the point that we were interested in. So since we're looking for the instantaneous rate of change at every single point on this table, we might as well go ahead and calculate the average rates of change so that we can then use them to talk about the instantaneous rate of change. Remember, the average rate of change is going to be f of b minus f of a over b minus a, which is the same thing as the change in y over change in x. So if we wanted to calculate the average rate of change between t equals 1 and t equals 2, we could do the change in y over the change in x. So we would do 16 minus 7, which is 9, divided by 2 minus 1, which is 1. And that would give us an average rate of change of 9. Similarly, if we wanted to find the average rate of change between 2 and 3, we would take 31 minus 16, the change in y, divided by 3 minus 2, which is the change in t, and we would get 15. Moving along, to get the average rate of change between 3 and 4, we would do 52 minus 31 divided by 4 minus 3, which would give us 21. And the average rate of change between 4 and 5 would give us 79 minus 52 divided by 5 minus 4, which is 27. So those are the average rates of change. But in this particular problem, I want the instantaneous rate of change. To get the instantaneous rate of change at 2, I'm going to use the average rate of change on the left and the average rate of change on the right, and I'm going to average those two numbers together. So 9 plus 15 is going to give me 24, divided by 2 is going to give me 12. So my approximation for the instantaneous rate of change at 2 is going to be 12 because I averaged the average rate of change on the left and the average rate of change on the right. Similarly, if I wanted to find the instantaneous rate of change at 3, I would average 15 and 21, which would give me 18. At 4, I would average 21 and 27, and averaging those together would give me 24. Now notice that so far I've deliberately avoided the endpoints because we have to talk about how we work with those since we don't have the option to look at the left and the right. So consider the instantaneous rate of change at 1. So since we don't know what's happening to the left of 1, the most accurate data that we have is what's happening to the right of 1. So we're actually going to use the average rate of change between 1 and 2 to approximate the instantaneous rate of change at 1 because we don't have anything to the left. Similarly, at 5, we're going to use the average rate of change between 4 and 5 because we don't have anything to the right of 5. So that would give me 27. So now I have an approximation for the instantaneous rate of change at every point on my table. But I want to say a little bit about some notation here. So we talked about how the instantaneous rate of change is the same as the derivative at a point. So that means that I could also write some of my information like this. F prime of 1 is approximately 9. So that says the instantaneous rate of change at 1 is approximately 9. I could write F prime of 2 is approximately 12. So that's the notation I would use to talk about the derivative at 2. I could write F prime of 3 is approximately 18. I could write F prime of 4 is approximately 24. And finally, F prime of 5 is approximately 27. So one of the things that we need to get comfortable with is that there's a lot of different ways to ask for the same piece of information. And there's a lot of different ways to write about the same information. So if we're talking about the instantaneous rate of change at 1, that's the same thing as asking for F prime of 1. The word prime represents that apostrophe that's up by the F. And I'm using approximations here because this is a table and I don't have an exact answer. This is my best guess based on what I have. So keeping these terms straight and knowing how to use them interchangeably is going to become something that we need to get really good at. So let's continue looking at examples of how we look for instantaneous rates of change and derivatives on different types of functions. Example 2. Using the graph of f of x below, determine if each of the following derivatives are positive, negative, or 0. One of the things that we want to get really good at is figuring out what the exact derivative is going to be based on a graph. In order to do that, the first thing we want to get good at is being able to envision the tangent line at a point and then using that to figure out if the slope of that line is positive, negative, or 0. So let's start with f prime of negative 2. So negative 2 is over here, and if I go to where the function is at negative 2, I have this point. So I'm imagining the line that touches only at that point. Now my line doesn't have to be perfect for this type of example. I just need to get a sense of where it touches. So here you can see it barely touches my point, but it's close enough for what I need to do. Because I just need to figure out, is the slope of my line positive, negative, or 0? Since my line is going downward from left to right, my line is decreasing there, I can see that the slope of that line is going to be negative. And remember, the derivative, or the instantaneous rate of change, is the slope of the tangent line. So if the slope is negative, that means that the derivative is negative. So I'm going to put a negative sign next to negative 2. So now, the next one I want to consider is what's happening at negative 1. So at negative 1, I'm considering the point that's here. And again, I'm trying to sketch in the line that touches at just that point. And it doesn't have to be perfect, right? We'll get better at these. And if you have this printed out, you can certainly use a ruler. So I'm trying to determine, is the slope of that line positive, negative, or 0? Since that line is going in the upward direction from left to right, the slope of that line is positive, which means the derivative is positive and the instantaneous rate of change is positive. The next one I'm going to consider is what happens at 0, f prime of 0. So again, I'm going to go to 0. I'm going to go to where that touches the function. And I'm going to sketch in a tangent line. So here's something really interesting happens. The line here looks like it's horizontal. And if your line is horizontal, that means that the slope of the line is 0. So that means in this case, my derivative, or my instantaneous rate of change, is 0. So that's going to happen whenever you have a horizontal tangent line. Now let's go to 1. So again, we're going to go to x equals 1. We're going to go down to where it is on the function. We're going to try to sketch in a tangent line. And we're going to look at whether we think that tangent line has a positive, negative, or 0 slope. Since it's going downward from left to right, the slope of that line is going to be negative. And then finally, we want to figure out what's happening at 2. So at 2, we're going to sketch in a tangent line here. And we're evaluating whether the slope of that line will be positive, negative, or 0. So the slope of that line is upward sloping, and that is going to be positive. Getting really good at determining whether the derivative is positive, negative, or 0 will lay a really solid foundation for the rest of this chapter and for the rest of this course. So if this is something that you're not comfortable with yet, I encourage you to practice this quite a bit, because if you can get this part down really well, it'll really help you in the future.